Okay, so hello again to those people that attended my ill-fated lecture last Friday. It's now Sunday, and because we lost the internet, I'm going to start all over and give the lecture. So what I'm going to do is share my screen and make believe nothing happened. And start over. So here we go. Okay, so the topic is isogeometric analysis. It will be introductory, and I'm going to describe mathematical aspects of this topic and engineering aspects as well. So I'll begin with talking about contemporary finite element analysis. It's had a long history, goes back to the 1940s. It's everywhere today. Everybody knows all about it, uses it for everything. But there are some shortcomings which lead us to the topic of isogeometric analysis. Then I'll go through a tutorial on basic technologies like B-splines and NURBS. There are more advanced technologies, but I won't talk too much about that. Maybe just show an example or so. Then talk about ways of getting our arms around the mathematical properties, functional analysis, mesh refinement techniques, H refinement, polynomial refinement on a fixed mesh, combinations thereof, and then the new secret weapon of isogeometric analysis, K refinement. That's what is really unique from the underlying technological point of view. So functional analysis gives you asymptotic error estimates. It gives you best approximations as these parameters are taken to 0 or infinity in essence. Kolmogorov n-widths, which I don't have enough time to go into, it's interesting in that it fixes the mesh. It says, or the number of degrees of freedom, say a Fourier series or something like that. And what it says is for an n degree of freedom system, what is the best you can do? What is the best n degree of freedom system? And it measures it on the basis of what is the worst best approximation. You have a target space, and if you have functions in that space that are not well approximated, that's what will define the Kolmogorov n-width. So in one sense, this is looking at the cup half empty. This is looking at the cup half full. Now, there are other aspects to isogeometric analysis that are noteworthy. One is the variation diminishing property of the basis functions, and I'll show how that comes up really in nonlinear analysis when you have things like obstacles, convex constraints, contact problems, things of that nature. Those problems depend on properties other than spectral properties. Everything up here is more or less looking at spectral properties. And one can do spectral analysis of meshes and really get a mode-by-mode understanding of exactly what's going on when you compute. You don't get that from classical functional analysis. You're getting asymptotic analysis. It's not telling you what's bad in there. It's telling you what's good in the limit. So these are all different ways of understanding approximation. Then we'll go into some problems, and the two main paradigms that are in use in this topic, namely boundary fitted modeling, the classical idea of building a model, and then there's trim and immersion, which probably actually precedes boundary fitting modeling historically, but on the other hand, it has only come into its own in recent years because of essentially a breakthrough in understanding how to get good accuracy with it. And then just say a couple of words about the future. So finite element analysis. Well, it's everywhere. Everybody does everything with it in every field, it seems. This is just an example of crash analysis with LS Dyna of a Mercedes, different configurations of crash analysis. Incredibly complicated models are used these days with anthropomorphic dummies, children dummies, adult dummies, different size. Airbags being deployed, as you can see here, seat belts being activated. So it's very interesting. Lots of contact, impact, things that can generate high modes in a discrete model. These are very, very large models. You do crash analysis of many things these days, surprisingly. For example, the iPhone is crash analyzed because they're getting dropped all over the place, and they have to be able to withstand that. Finite elements in CFD, also widely used in industry. This is a Dassault Falcon. Finite elements are used at Boeing to design airplanes, and very successfully, I might add. So you can do complicated topologies and geometries. And then in recent years, computational medicine has become a big topic. And this is an example from Alberto Figueroa at Michigan. And it's a 100-vessel model of all the main arteries. And they are discretized in detail in 3D. These are not sticks, these arteries are little flow channels. These are 3D objects that are fluid structure models. So you're solving the Navier-Stokes equations inside all of the vessels, and you have tissue varying material properties for the walls of the vessels. And of course, the viscosity varies too, because really blood is non-Newtonian, but you can model that by Newtonian over different segments, but with different viscosities. So here you see the detail of the mesh. This is the triangulated surface mesh. So this is the outer wall of the arteries. This is the aortic arch right here, as you can see. And these elements are prismatic, and they go in a layer just to model the wall. And then inside, it's all tetrahedra. So very large models. And here's just some results of flow pressures and volumetric flows, as you can see here in various places. It is fluid structure. You can see the walls are moving here, the whole model. So these are the types of things you can do. This is good for studies of like tilt tests. You can tilt the whole body and ask questions about the reactions of the baroreceptors. So that looks great. What's the problem? Well, it takes a long time to generate those models. It's a big bottleneck in industry. And to facilitate the generation of those computational models, you introduce many geometric simplifications, in other words, errors, and sometimes they're extremely influential. And that's done by removing features and so-called geometry cleanup, and I'll explain a little bit more about that as we go along. So this is a problem. Its severity is actually quite great because, as you'll see in a moment, it's more time consuming than analysis. So another is closing the loop with design optimization. In design optimization, you have to talk to the source of the data. It has to be completely integrated with the analysis. And that requires in industry talking to CAD directly. So CAD and finite element analysis have to be intimately integrated, and they're not. So that's a problem. If you're going to revise the geometry, you have to take results from the finite element analysis and go back to the CAD system and just sort of manually change things. Now, finally, in the pure analysis sector, the promise of higher order elements that you hear a lot about in academic papers, it has not been realized in industry. The most widely used commercial and industrial finite element codes rely on lowest degree elements, specifically bilinear quads and trilinear hexes in solids and typically linear triangles and tetrahedra in fluids. So why is that? We're going to see. So here's just a flowchart of the engineering analysis process. And this summarized a lot of data that was developed at Sandia National Laboratories. And a very famous report was the DART report. And this picture essentially emanates from that. So you're creating your finite element models, your meshes, from CAD representations. And it turns out that the overall process of doing that consumes more than 80% of overall analysis time. And this was over many different types of analysis that are done by numerous analysts, thousands at Sandia. And this really constitutes a big bottleneck in industry. And again, in the process, you introduce a lot of geometry approximations that can lead to substantial inaccuracies. So what's the problem? Why does it take so long to do this? If you look at a simple part, this is a one-piece B-pillar. So this is a piece of sheet metal that is cut, bent, holes are drilled into it. And it's relatively simple. You would think you could generate a mesh for that in a very small amount of time. Actually, it's not too hard to do that. But with all those little features, it becomes very, very difficult. Well, those pictures you look at in CAD are masked. They are computer graphics. The data structure is much more daunting, as you can see here. The data structure consists of images of rectangular patches that are intersected. And each patch, part of it is representing part of the real geometry, and part is just cut away, trimmed away. And you can see for this one piece here, there were 1,280 mappings of these rectangular patches. So you have 1,280 trim surfaces where you have a cut through each one. And along those trim lines, they're not watertight. They're not linked, okay? They have gaps and overlaps. So that becomes the problem of mesh generation. This is just a part, but imagine doing an airplane or a car, full detail. All of those issues have to be corrected in order to generate your model, and it's very time consuming. So isogeometric analysis was really developed with the objectives of dealing with that problem of model development. It started off completely as a model development idea with similarities to finite element analysis. And the initial hope was it was just maybe as accurate as traditional finite element analysis. But what we found is it's much more accurate, in fact. But the idea was to reconstitute finite element analysis within CAD geometry, use the CAD geometry, make that fundamental to analysis. And then you will simplify the model development problem thereby. Sort of you're breaking apart this gap of these two different classes of technologies and integrating design and analysis. So that was the idea. So it started with a paper in 2005 that I wrote with two of my then students, Austin Cottrell and Yuri Basilevs. And it started to take off. And as of March 22nd of this year, according to Web of Science, which gives you always the lower bound, there were over 3,600 papers, over 86,000 citations. So it's gotten a lot of attention. And actually the growth rate of isogeometric analysis is much faster than for finite element analysis, which seemed to sweep away the world. But it took a long time for finite element analysis to do that, depending on where you place the start, say the 1950s or 60s. And what is it? It's based on computational geometry technologies used in design, animation, graphic art, and visualization. And these technologies are extremely rich. They are much richer than the polynomial basis of finite element analysis, at least as it existed up to the invention of isogeometric analysis. So it includes finite element analysis, but includes these other possibilities as well that become essential to the benefit of isogeometric analysis. Precise and efficient geometric modeling, simplified mesh refinement algorithms, smooth basis functions with compact support so you can go directly after higher order PDEs, superior approximation properties, as you will see, and the integration, of course, of design and analysis. From a finite element perspective, isogeometric analysis represents a superset of technologies of classical finite element analysis. In finite element analysis, you have two basic refinement strategies. One is mesh refinement, and one is polynomial or order refinement, elevating order. In isogeometric analysis, you have K refinement. And that is a technology in which you increase order, but simultaneously you increase smoothness. And that turns out to be the secret weapon of finite element of isogeometric analysis. So let me give you some insight into the technologies that are used, because in some sense, B-splines and NURBS are common underpinnings to all the different more elaborate technologies now, the unstructured spline technologies like U-splines and S-splines, T-splines. So the elegant way of generating B-splines on a one-dimensional domain is to partition it into so-called knot spans and recursively define the polynomial functions on the patch. And you start with piecewise constants, and then you use the Cox-de Boer recursion relationship to go from constants to linears. Then you put the linears on the right, and you can generate quadratics and so on and so forth. And if you start with any uniform knot vector, and you use those, the Cox-de Boer recursion, you will get something looking like this. These are the constants on the knot spans, then you get the linear hat functions. And then when you go to quadratics, it no longer looks like finite element technology. You get smooth basis functions that are pointwise positive, okay? They're monotone. And as you can see, in going from constants to linears to quadratics, each order increases the number of knot spans. And in addition, you've increased the smoothness from C-1 to C0 to C1. Cubics would give you C2 continuity, cortex C3 continuity, and so on and so forth. Always positive, pointwise positive. So this is just an example to give you an idea what you can do. You can start with sort of a uniform distribution of knots. But if you have multiplicity p+1 at the ends of the patch, you become interpolatory there. So the value of the function would be 1. You can repeat knots. They don't have to be equally spaced. You can also repeat knots, though. And when you repeat a knot, you lower the continuity by 1 degree. So here we went from the natural C1 continuous quadratic splines to C0 continuity here. Okay. And again, if I repeat once more, I will split the patch into 2. I'll completely disconnect them. So this is a free-form object. You take that basis, you multiply each basis function by coordinates in the plane, a coordinate vector, so the so-called control points. They control the shape of the object. And you can see where they're placed, and just connecting them linearly, that's the control. It's called the control polygon. In 1D, it's really a control mesh, but in any event. And as you see, it's smooth everywhere, just like the basis functions, except where it's only continuous right here. And not only is it interpolating the endpoints, but it's interpolating that point. So all those points are interpolatory points, but elsewhere it's not interpolatory. Now, the nice thing about the monotonicity and positivity of the functions, as you drag the points, you change the shape of the design, and you do it monotonically. I mean, obviously, that's crucial in design. You wouldn't want oscillations being introduced by moving a control point. But if you did that with interpolatory polynomials, that's exactly what would happen. So these are good. And there's a dual picture. And what it is, it's really the deconstruction of the computational geometry data structure into a finite element data structure. And that is facilitated by so-called Bézier extraction. So you break it up into elements, and you can build this entity with polynomials. We use Bernstein polynomials on each element, and you can assemble them back smoothly. So these two pictures are exactly the same object, parametrically and geometrically, and yet they represent two different ways of creating a data representation of it. So this is important for analysis. This is important for design. And you can refine the mesh. So what we've done here is we've bisected the mesh by introducing knots halfway between all the other intervals that were there. And as you can see, the geometric object has not changed at all. It's exactly the same. So this is really important. When this is unlike finite element analysis. In finite element analysis, you have to find the geometry. The geometry is a separate entity from the mesh. The mesh is an approximation. So you can't just refine the mesh without looking for the geometry to know where the other points should be. So again, it's we now have a finer mesh with the same geometric object. The geometric mapping has been fixed, and we can get a more accurate result if we were to do analysis. And we can go on and do that again and again, as you can see here. And you have a notion of p-refinement. You start with a basis again. We'll go back to the beginning. Now we're going to fix the mesh, but we're going to increase the order of polynomials on each of the elements and maintain the continuity that's there. So that's p-refinement. So the mesh is the same. We started with quadratics. Now we're up to quartics, but the continuity is the same. It's still C1 continuous everywhere except this point here where it's C0. So you've seen some of the free form modeling capability of splines, but in engineering analysis, you need precision. So you need exact circles, obviously for shafts and holes and things of that nature, as you can see in these objects. And you need conic sections, exact ellipses. And you can get those with NURBS. And NURBS are rational B-splines. So you have a B-spline in the numerator, a B-spline in the denominator. So you have a rational function. And then through a projective transformation, you can create conic sections. So this is just an illustration of one way to construct an exact circle explicitly by projecting 4 quadratic B-splines in a higher dimensional space. So that's the power of NURBS. So this is a NURBS object. It's an exact torus, an exact circular torus. It consists of 16, call it quadratic elements, but they're rational quadratics. And this is the control net. And you can H-refine it, as you see here. Now we've got a much finer mesh, and the points, the control points are converging on the object. You could, again, adopt the P-refinement philosophy, go to higher and higher order, from quadratics to cubics to quartics, the same mesh, the geometry map doesn't change, but you have a higher order basis now on that geometry. And this is just a 3D example of a pipe elbow modeled with quadratic NURBS, so you have exact circular arcs there. And you can see the control net on the left. Okay, so the important transformation, as I indicate, is Bezier extraction. And from all the technologies that exist in computational geometry, you can go from those and their, let's say, natural data structures within that realm to a finite element data structure. And of course, then you can build finite element codes and run these in somewhat modified finite element codes, but not dramatically modified in any sense. So this is a powerful way of thinking about this and bringing all of the computational geometries into the domain of finite element analysis. So what are the similarities between traditional finite element analysis and NURBS-based isogeometric analysis? Well, as you saw, the functions have compact support. You didn't see this, but they sum to 1, so they have a partition of unity property. They possess affine covariance, meaning if you move the control points consonant with an affine transformation, every point in the object does that. That's not entirely obvious when you're dealing with rational functions, rational polynomials, but indeed it holds. And then in mechanics, if you invoke the isoparametric concept, all patch tests will be satisfied. Now that's important from a convergence perspective to engineers, maybe less so to mathematicians. But on the mathematical side, you also have error estimates in Sobolev norms. And maybe those are a little less of concern to engineers, but of prime concern to mathematicians. So what are the mathematical properties, and what are the ways of looking at it? Well, as in the introduction, there are functional analysis techniques, Kolmogorov of n-widths, sort of giving you a different insight into your approximability, spectral analysis, which I'm going to spend a little time on to show you what the issues are there, and then the variation diminishing property, which pops up outside of the realm of spectral analysis when you have inequality constraints on, say, control points or degrees of freedom. Then results depend on more than the spectrum. They depend on things like monotonicity and variation diminishing properties. So this is the fundamental error estimate approximation result, I should say, in Sobolev norms for H refinement. And again, the order of convergence is exactly the same as you would get for traditional finite element analysis with the same order of functions. So it doesn't look like anything's different, but there's a lot hiding in the proverbial constant. It depends on the polynomial order, it depends on the smoothness of the space, which is a differentiator, and shape regularity of the mesh, et cetera, et cetera. Well, once you have this, you can prove theorems to your heart's content, and that's been done. So there's lots of that around, as you can see from some of the references below. Now, this sort of summarizes the story in one picture from a functional analysis point of view. It's just giving you an error estimate in Sobolev norm of a function that has a certain amount of smoothness. And the idea here is what happens when you vary the smoothness and you vary the polynomial order. And of course, you have to have enough smoothness of the target for these results to be meaningful. But we're assuming maximum regularity. So the regularity is p+1. Now, what we have here is too many curves, I will admit, but let me tell you that the accuracy increases as the points drop. And so you can look at it in different ways. You can fix the smoothness. So let's say we fix at C1 smoothness for splines. And you can see if you do that, you get better accuracy as you increase P. P is higher as you drop. So P is 1 up here, P is 10 down here. So that's kind of obvious. Polynomial order is higher on a fixed, for a fixed continuity, you get better accuracy. On the other hand, you can fix P and run along one of these curves. So I'll run along the bottom one since it has the most information. That's for P equals 10. You start off with discontinuous functions, then C0 functions, C1 functions. So these are sort of like traditional finite elements. But you can see again, as you increase the continuity going to the right, you get better and better accuracy because you're dropping. And you drop the most when you go to full continuity, CP -1. Okay, that's the maximal smoothness for a p-th order spline. So that's where the bang for the buck goes, and that's associated with what we call K refinement. And just to repeat again, all traditional finite element analysis lives down here, with a few exceptions that are here, but it all lives down here. So you can do better, is what the message is here. Okay, so let's look at an example. An elastic plate, infinite plate with a circular hole under uniform tension in the x direction of magnitude 10. And we'll look at H refinements to start. And this is just a square domain, consisting of two elements. This is a circular hole, not an approximation, it's exact. We're using NURBS here. And then we have just bisection refinements, as you see here. So the geometry is exact and it's fixed throughout the refinement. These are just contours of the X stress. And if you're familiar with classical results in elasticity, you know at this point here, you get maximal tension, and it's 3 times the applied load, or 30 in this case. And you see the stresses are very nice because they're smooth functions. This is the error in L2, the L2 norm of stress, I should say. So that involves derivatives. It's like H1. And what you see is the convergence rates for quadratic, cubic, and quartic maximally smooth splines. So this picture is exactly what you would expect from the approximation result that I quoted. And you would expect the same thing for C0 finite elements. We don't have them plotted here. The slopes would be the same, but the curves would be higher up. They would be higher up. And this is, at least if you equivalence things on degrees of freedom. So when you H refine, though, and you're going to the left here with H refinement, you're incurring a much bigger problem. The number of degrees of freedom is increasing. That's kind of obvious. Now, K refinement is a little bit different. And in K refinement, what you're doing is you're essentially fixing the mesh. Now, in contrast, P refinement uses a fixed mesh. But what you do is you maintain continuity. So it's C0 continuity here over 3 elements. These are Bernstein polynomials. So it's C0 continuity. You elevate the polynomials from quadratics to cubics to quartics to quintics, and you get more and more functions, as you can see. And in K refinement, again, you keep the mesh the same, the order of approximation the same for pairs here. But as you refine, you increase the continuity and you get many fewer functions, as you can see. If you take that out to a big mesh, it's quite dramatic, the increases. Now, what this technology gives for you is something that we never had in finite element analysis. Namely, we never had geometrically adaptable functions that were smooth with essentially any order of smoothness we were interested in. We had C0 finite elements, we had discontinuous finite elements, but and a few and far between C1 finite elements. But now we've got the gamut. And this paradigm doesn't require derivative degrees of freedom at nodes. You have the ordinary degrees of freedom. And so it really is giving a completely new opportunity in analysis. And there's still many, many unexploited possibilities for its use in analysis. So that's part of K refinement and isogeometric analysis. So let's just count up number of degrees of freedom when you refine a mesh by these 2 techniques now, classical P refinement and then K refinement. So you start with n basis functions in 1D of order P, and then you do R refinement levels, okay? And then the number of basis functions, which are each now of order P plus R, is n times R for P refinement, it's n plus R for K refinement. That's very different, and if you cube it, as in 3D, you get these dramatic differences. You start, say, and this is just dramatized, of course, but you start with a mesh in 3D of n cube points, say 100 cubed, so 1,000,000 points. You refine 10 levels of refinement or order elevation in P refinement, and you go from 1,000,000 degrees of freedom to 1.3 roughly billion degrees of freedom, factor of 1,000 increase. You do the same with K refinement on the same mesh, 1,000,000 elements in these meshes, and you do 10 orders of refinement. And now what do you have? You have 1.3 million degrees of freedom, 1,000 times fewer. So you've got the same mesh, the same order of approximation, and you have many, many fewer elements. So if that kind of suggests if we would equivalence the number of degrees of freedom, we might have a much more efficient technology over here. And that's the case. So K refinement works this way. You're essentially keeping the number of degrees of freedom constant. They're only changing at the boundary. And that is obviously a domain of lower dimension. So you're almost dropping vertically across these curves. On the same mesh, you're going from here to here to here, very slight slope outward. And you can see, incurring roughly the same number of degrees of freedom, you're picking up accuracy jumps of orders of magnitude. And it really works that way. Now, it looks like when you're going to higher and higher order, your knots, your basis functions, they are spanned by more knots. And it looks like that might engender a wider bandwidth for a matrix system. But in truth, for the same order of basis functions, it's exactly the same as C0 finite elements. So here you have a bandwidth of 7. This is a C0 finite element. It's coupled to 3 on the left, 3 on the right. Again, you have a bandwidth of 7. The band profile structure, the outer band profile structure is the same, but within the band, you do have a denser structure here, which is, well, it's a drawback for direct solvers, and but it's actually beneficial for iterative solvers. You have more coupling. So let's look at spectral analysis, and that will give us insight into the entire spectrum that we're working with when we discretize an object or structure or fluid domain, whatever. So we're going to look at the simplest eigenvalue problem, the second order operator in variational form, just using classical Galerkin method. And we're going to compare finite elements and isogeometric analysis. And the error estimates that are, at least 50 years old are the same for both. So if you have a 2s order differential operator, then this is the rate of convergence of the eigenvalues, the eigenfunctions. L is the mode number, the eigenfunctions in the energy norm, and the eigenfunctions in the L2 norm. Now, the interesting thing here, though, is the estimate is dominated by this term here. As you reduce H, you get better approximability. But H times the eigenvalue to this power has to be smaller than 1 to get convergence. So that becomes a smallness condition on H, because lambda in the higher modes is getting bigger and bigger. So this really doesn't tell you what's going on in your analysis in the high modes. It only tells you asymptotically, as H goes to 0, what's going on in the well-resolved modes. Now, another picture can be created by a budget of these errors, an identity that relates the eigenvalue error, the square of the L2 modal error, and the square of the energy modal error. And this is what I refer to as the Pythagorean eigenvalue error theorem. And this is exact for every mode in the mesh, not asymptotic, it's exact. And this is an example now. C1 continuous B-splines, P equals 2. And this is the spectrum. So if I have divided the domain into 100 elements, 1,000 elements, 1,000,000 elements, that's n. And then this is just the mode number, small n. So in the middle, you have an error, some very small error here, less than 1% or order of percent in these quantities. But you've got very, very good accuracy, at least from a plot standpoint, up to about 0.4 for these quadratic B-splines. And everything's color coordinated, so you can see this is the L2 error squared here in the mode. This is the eigenvalue error in red, and then the sum is the square of the energy norm error. Okay, so that's your entire spectral content. And it's what you would expect. Accuracy in the low modes. Okay, that's what you're getting from the asymptotic results. And then deterioration in the high modes. Okay. Now, if I did this with C0 finite elements that were quadratic, you'd expect a similar picture, but you don't get it. You get some real surprises. And we've known for a long time that there's a bifurcated spectrum. You get an acoustic branch and an optical branch, and the optical branch has no approximability. This picture for the eigenvalues is in my old finite element book even. But what we found as a surprise when we investigated this more recently was that we got errors in the L2 eigenfunctions that had very weird behavior at certain mode numbers, in the neighborhood of certain mode numbers. We got spikes, as you see here. And then again, the sum is up here. So much worse per degree of freedom than over here. And the high modes are complete garbage here. And as you go to higher order, let's say we go to higher order now on the splines, we're going to use the K refinement philosophy. We go to C2 continuous cubic splines. And you can see those curves are being pushed out to the right. So we're getting more accuracy. Now the accuracy is really good, right up to 0.6, and then it starts to deteriorate. Now, if we look at the C0 finite elements again that are cubic, we get this picture here. And now we have two little spikes in here, and these things are getting worse. They're not getting better. You would expect them to get better. They're not. They're getting worse. And if you do it again, the splines are getting better. Finite elements are getting worse. If you add these two curves, if you're really off the page with the errors here, that's how bad they are. So what's going on? Well, this is the square root of the eigenvalues. But what you can see here is, and you can prove it analytically and mathematically, that this part of the spectrum, these, let's say, optical branches, are diverging with P. So as the lower modes are getting more accurate in the asymptotic regime, the higher modes are completely degenerating. So you have a lack of robustness account of that, because if you activate these modes, they generate errors throughout the mesh. You get poor conditioning as well. Here are linear finite elements. There's only an acoustical branch for linear finite elements. Maybe that explains why they've been used so widely for difficult problems. They don't have these pathologies that C0 finite elements do. But as you go to higher order splines, NURBS, you're getting, in essence, almost spectral convergence here. Big jump from linears to quadratics, significant jump to cubics, and then less so as you go up. But again, you don't have these optical branches. And if you understand this picture, you will understand why on hard problems, C0 finite elements cannot work, because these terrible modes, these inaccurate modes get aroused, like in blast and in contact and impact, whereas you don't have that with smooth splines. In fact, as you go to higher order, you become more robust. We wrote a paper on that and showed that. We did all sorts of torture tests and showed that higher order spline bases give you more robustness as you get to higher order. Okay, what about the variation diminishing property? Well, I gave you a little bit of insight into that. Actually, if you just look at interpolation, you get an idea of what the problem is. If you have a set of data points representing a discontinuity and you have interpolatory polynomials like Lagrange polynomials, which are widespread in finite element analysis, you get oscillations like that. And you can't get rid of them if you're interpolating. If you add more points, you get the same overshoots and undershoots, you just get higher frequencies. Now with NURBS, these are controlled by control points, and you get a variation diminishing fix. You get no new extremer, as you can see here. So as you go to higher order, you're actually smoothing things out. If you wanted a smooth step function, a smoothed out version of a step function, if you put more points here, that's exactly what you would get. You get nothing like that over here. And this has benefits in contact problems. And the first time we ever saw this is when these ideas were being implemented in LS-DYNA some years ago by Dave Benson. And this is a crash benchmark problem in which you have a hollow tube modeled with shells, and you just are crushing it into a wall. It does have an imperfection to get the let's say the bifurcation to this unstable branch initially to initiate it. And you can see this problem is just dominated by plastic deformations and contact especially. And the splines here are C3 continuous cortex. They have a knot span of 5 of these elements you see here. And this was the first time that this problem was ever solved with higher order elements. And it just gave one an insight into the potential of these methods because of robustness. So let me just give a few applications now. So we're looking at the modeling paradigms, the classical one, boundary fitted modeling. We'll start with wind turbines. And what we'll look at is some work of Ming-Chen Su and his colleagues. And this is a wind turbine. This is a design platform based on the visual programming language Grasshopper, and utilizing the CAD system Rhino as the geometric model underneath. So you're building your geometric model of the shell structure, and you're parametrically changing it for whatever objectives you have. So it's an optimization loop is in there too. And this is a composite structure. It has many different internals. It has all sorts of materials and all sorts of composite layups for each individual piece. So it's a real structure, and it's being analyzed with classical laminated shell theory, both with finite elements and with splines. And the finite elements were done with ANSYS, with traditional C0 4-node finite element technology, degree 1. And that's the blue curve here. It's actually a buckling mode, the first buckling mode. And that is the thing you're looking for. And with the traditional technology with a mesh here, that is actually about twice as big as the design mesh, maybe 15,000 shell elements. It's converging, as you can see, as you refine the mesh, and you sort of reach convergence at about 400,000 elements. The red curve is isogeometric analysis with Kirchhoff-Love rotation-free shells. These are degree 3, but there's actually half as many degrees of freedom in this mesh than there is in the traditional 4-node shell element mesh that's degree 1. So here you have 8,000 elements, approximately 24,000 degrees of freedom. For this mesh over here, with the finite elements, you have about 400,000 elements with 6 degrees of freedom, so 2.4 million degrees of freedom. Let's see, 8,000 to 400,000 times 6, yeah, 2.4 million versus 24,000. Okay, so you've got basically 3 orders of magnitude difference in the number of degrees of freedom. This takes minutes. This takes significant computing time. And the accuracy you get really in the design mesh is adequate, for most engineering purposes. So that shows you how you can integrate design and analysis and get very, very fast analysis. Because in that case, that previous case, your design mesh is your analysis mesh. You use the CAD file as your analysis mesh. So what this here is now, this is an example from Coreform. It's a flexible cable. It's a composite again, 9 layers of different material, very large deformations. And what you're worried about here is delamination. And as you can see from this cross-section here, this is a finite element model. This involved 10 million volume elements. This one was done with Abacus, and the client was using Abacus for these analyses. But with 10 million volume elements, it got expensive. And this is a U-spline mesh, that's Coreform's technology of unstructured splines. And you can see not only are they unstructured, but you can have T-junctions, and you are smooth across those T-junctions. So you can have smooth discretizations, even with T-junctions and extraordinary points and things of that nature. So, okay, so what's the upshot? The upshot is everything is smaller and faster. In the end, you can solve these problems about 1,000 times faster. This took 73 core hours, and this took 72,000 core hours. And you even have a more accurate result and better geometry. So, okay, so that's when you use the traditional modeling paradigm, but trim and immersion are playing a big role with isogeometric analysis right now, and they will play an even bigger role going forward, in my opinion. So what's trim? Trim is essentially what you're using in CAD. It's sort of a phase field. It's a phase field where you have an object. The object sits in, say, a box, a parameterized box, and you have 2 phases. One phase is, say, 1 for the object, alpha equals 1, and one phase is 0, or a very small number, for what's left behind. So this is the same as CAD. And historically, what these methods suffered from is inaccuracy on the cut cells. It was very hard to get any kind of accuracy, but there was a breakthrough some years ago, and it was developed by Ernst Rank and Alexander Duster at TUM. And what they discovered is you really precisely integrated the cut cell integrals in say a finite element or an isogeometric analysis formulation, you could get the full accuracy of whatever approach you were using. And you could even get things like P convergence, exponential convergence. And here's just an example. And this mesh actually conforms to that picture. It's just a 6x6 mesh of elements. And what you're doing is you're solving the hole in a plate. And these are all cut cells here. So you got a square mesh, and they're just being cut by the actual geometry here. And we just refined to 12x12 and 24x24. And what these analytical results are up here is the circumferential stress, the hoop stress around the hole. And this is the distribution of it. So what you're getting is point-wise convergence of these quantities. They're not inaccurate, they're accurate. and you're getting them right on the boundary of the cut cells. That makes all the difference, and that's drawn a tremendous amount of attention now to these approaches, because you can build models with trim and immersion so simply. So here's an example again of trim. This is an oil sump. You can see it's a shell-like structure. And this is a trimmed CAD file of the structure. This is the untrimmed CAD file. You're seeing the data structure there, the stuff that's trimmed away. And now you take your trimmed CAD file. It's going to be your analysis model. And you can refine it just by knot insertion on each of the patches. The patches are joined together by Nietzsche methods or penalty methods or Lagrange multipliers. But now you have a very, very refined mesh, good for analysis, and you never left the geometry of CAD. You're in CAD, that's a CAD model, but it's also the analysis model. And here are some results. We've already beat up on ANSYS and Abacus, and now it's Nastran's turn. This is a Nastran analysis over here with 855,000 degrees of freedom. This is a cruder IGA model with 160,000 degrees of freedom and stress results plotted on the mesh in this area right here. As you can see, you're getting much smoother stresses. You have a really nice geometry. In fact, you have the exact geometry. And over here, you have this faceted arrangement and bigger jumps between the stresses. So, okay. What else? You're in CAD. You're in CAD all along. So if you deformed your model and wanted to change your design, you haven't left CAD. It's very, very easy to do. So you've closed the design analysis optimization loop. So what is immersion? Immersion is just the three-dimensional terminology for trim. Suppose you have a wheel. You know, wheels are solid. Okay, so you have a solid wheel and you want to analyze it. It's hard to mesh. What you do is you drop it in a box of B-splines, and then you throw away essentially the elements that are not intersecting the object. Here they are. All these elements are cut cells. You do mesh refinement, adaptive, local mesh refinement, wherever you like. This is your quadrature grid to give you the accuracy in the cut cells especially. And you get a 3D analysis. And it's essentially an automatic procedure. You don't have all of this complexity. You just take the CAD file and drop it into the box. And that technology is being developed in many interesting ways. But again, this is sort of the same idea. This was from the Ernst Rank group. This is a very, very complex bracket. It has many gaps and overlaps between the CAD patches. Before so-called healing comes in to try to fix that, there are over 3,000. Even after using the best healing software, you still had 250. So it's really difficult to generate a traditional boundary fitted mesh for something like this. I guess maybe you could do it with an enormous amount of effort and time, but why do that when you can drop it into a box of B-splines and use the same approach and get a very nice result and good accuracy? Okay, let me show you an example that sort of illustrates, I'd say, both the ideas of boundary fitted and immersed modeling. And maybe this is the future. And the core form technology, this is not core form's work, this is our work, but the core form technology now is called Flex, and it combines boundary fitted and immersed modeling all in one. But here's an analysis of a heart valve, an aortic valve. It's modeled with 3 leaflets. The leaflets are done here with NURBS. And what you can see is the leaflets are attached to the aorta. The aorta is modeled as a 3-dimensional solid, okay? And it's nonlinear, it's a hyperelastic material. And as the heart pumps into the aorta, it expands the wall, as you can see, so it's deformable. And we're solving the Navier-Stokes equations in 3D. on the mesh inside. And of course, that mesh is an arbitrary Lagrangian Eulerian mesh. It's moving with the artery wall. Okay. Now, what is happening in the interior is the heart valves, they're obviously undergoing very large deformations and closing. You got contact through the fluid. They have to close completely to prevent regurgitation. And they are moving through a moving background mesh. The background mesh is moving with the walls, and they are moving through that. So you have immersed shell, you have, and the fluid mesh and the solid mesh, everything's moving. And all of these different technologies are combined. So that kind of is a peek into my vision of the future. I think the future will obviously be a continuation of the present. So computational medicine is a growing technology. It's popping up everywhere. We're working in several different areas. It's occurring all over the world. It's becoming a big commercial field as well. So there'll be great things coming from this. Phase fields. Phase fields are everywhere. We never recognized it, but CAD is a phase field. It's just a binary field. You have material and you don't. And you can do analysis with that now directly. And you can do immerse methods, the three-dimensional version. Topology optimization is a phase field. You turn on the material where it is and you turn it off where it isn't. Additive manufacturing, the same thing. And the phase field can have gradations in material properties, as is essential in additive manufacturing. Multi-phase flows. Even fracture has undergone, I would say, a renaissance due to phase field methodology. I see in the future significant efforts towards speeding up the overall design through analysis process and bringing manufacturing in. So I think isogeometric analysis is a key enabling technology for doing that. Now, of course, the elephant in the room these days is machine learning applications in design and analysis. And so far, what I'd say is in design, you see quite a bit. In analysis, and many efforts in design in industry. In analysis, less so. It's more traditional finite element type methodologies, including isogeometric analysis. That may change. Now, of course, in analysis, you've had reduced order modeling for a long time. And that, in a sense, is an example of machine learning, but it's not, let's say, the full-blown palette of possibilities in machine learning. So that remains to be seen what's going to happen there, but there's a lot of effort taking place right now. I think HeartFlow is an example of a company that illustrates this combination and this dichotomy between machine learning and traditional analysis techniques. They do coronary disease diagnosis virtually by doing analysis of patient-specific coronary anatomies. So you'll get diseased blood vessels, and what you're doing is measuring. You solve the full Navier-Stokes equations, and you get the pressure drops. And in essence, the pressure drop is called FFR. When you do it virtually, it's called FFR-CT. And that's what they offer, a non-invasive technology to give you the gold standard of coronary disease diagnosis. Here at 0.6, this person needs an intervention. If it's below 0.8, you need an intervention. So how do they do all this? Well, they go from medical imaging, CT scans of the heart and the coronaries, and they have deep learning technologies to generate the luminal boundaries of the vessels, the outer walls, the diseased areas, et cetera. And yet they use finite element CFD. In fact, they use a technology that I developed for them many years ago. And they use that to compute the FFR, again, non-invasively. So they're still using finite elements over on the analysis side, but they're using deep learning on the geometric, let's say, design or modeling side. So you're seeing a lot of that. It still is, the jury is still out on the utility of deep learning on the analysis side, although you can clearly have some successes in certain specific applications. So, I've been in sort of the finite element business for a long time. I got initially exposed to it in the 1960s and then did a deep dive thereafter. It's interesting that at that time, there was ferocious resistance to finite element analysis. It was just incredible, some of the battles we had when I was working in industry at the time. But eventually it all came to pass. It takes a long time. It was interesting in starting with isogeometric analysis because I felt I was reliving my past. There was a lot of resistance, an enormous amount of resistance. There still is resistance, but a lot of it's gone away. But the people that were really initially resistant still are to a certain extent to isogeometric analysis are the finite element people. So they were born with finite elements. They learned it as kind of the gospel, but it wasn't the gospel when I learned it, believe me. So we had this resistance to these new ideas. And I like these words of Arthur C. Clarke about how new ideas pass through 3 periods. It certainly happened for finite elements. It's already happening in isogeometric analysis. But the first is, it can't be done. And then the second is, it probably can be done, but it's not worth doing. And then the third and final period is, I knew it was a good idea all along. So I think that was the way it was with finite elements. I trust that's the way it's going to be or is with isogeometric analysis. So with that, I will thank you for attention and again, apologize for what happened on Friday when the internet went down. We couldn't complete the lecture. I hope this is, at least in a small way, will give you an idea of what I was going to talk about then. So again, thank you very much. There's no possibility with a recorded lecture to answer questions directly, but if you send me an email, I'm easy to find. Just look for Thomas J.R. Hughes on the web and you'll find my affiliation and coordinates, and then you can contact me and I'd be glad to communicate any way you like, by email or Zoom, on any issue that's of interest to you. So again, many thanks, and I guess that will end the presentation. So let's stop the share and end the presentation.